Hi, how's it going? Here's what we've got at the moment from the last video. It's nice. It's a cube. Okay, let's go ahead and add lighting. To start with, we'll need to, I'll just clear everything all off. We'll need to create a light class. There we have it. So as we can see, this is very simple. We're pretty much just storing information. We could move it around, update the light, but I'm just going to keep it as at a fixed everything, basically. Okay, so we'll go ahead and now create the CPP file for that, the definition. Okay, great. That's all we need. We're just grabbing some info. Okay, so now we'll declare the scene and set it up with, well, we'll go with a set of lights, and at the moment we'll just put one in there. Okay, that's looking good. Then we'll just create our single light. Okay, that's looking good, and we'll also destroy that. Okay, so now let's head to the engine and take that info, put it in. Okay, perhaps this needs a bit of explanation. So we're going to define a light structure in our shader, and that light structure will have a color field, position field, and strength field. So because we're going to be updating that information every frame, we'll grab locations to that info ahead of time. Also, we're going to get the camera's position and send that to the shader, because in order to get the specular reflections, that also depends on which position the camera is when they're looking at an object. Good, so now we'll go to the definition here and we'll actually get those locations. Okay, so what we're doing here is we're going to have a uniform called light, which is of that structure, and the structure is going to have 3 fields, and these will be their names. So we'll access them by light.color and so on. So surprisingly, we're making a lot of progress at the moment. What we'll need to do is go down to the render section and pass the information in, pretty much like we're doing here. So we'll get the camera location in there first. Okay, so there we have it. We're passing that info in. We will need to now program our shader. So we'll just go back to the shaders and we'll start with the vertex shader. So the vertex shader will take all of this, but in order to do lighting, we'll also need to take normal attribute. And then we're going to put out the texture coordinates still. The fragment position, that's in world space, not screen space. And the fragment normal as well. Okay, now in order to get the fragment position, we'll take the model times the position, and we'll need to cast that to a 3D vector. So we'll get that and take the XYZ components. Okay, fair enough. We take the vertex normal, transform it by the model, but we'll also need to cast that model to a 3x3 matrix. Remember, in a full 4x4 matrix, the upper 3x3 square matrix simply has rotations, and the rightmost column has translations. So all we want to do is rotate the normal, which is why we're going to cast this to a 3x3. There are more complicated formulae, but this is a shortcut if we're not doing any scaling. By which I mean, if we're not doing any scaling, we can get away with using this shortcut. Now it's probably worth noting, we'll go to the object, where are we? Object mesh, and just check that we are loading in the normal data already. So yep, we have position is attribute 0, texture coordinate is attribute 1, normal is attribute 2. That matches up here. And we have set this properly. So we have, what is it? 3 numbers. Yep, that's right. Okay, good. Just double checking. Yep. 3 numbers for position, 2 numbers for texture coordinates, so that's 5, and then another 3, so that's 8. And that makes sense because we're dividing the number of things by 8 to get the number of vertices, because every 8 numbers is 1 vertex. And if we check through this, this all matches up, so that's great. We've done that ahead of time. That's good. Okay, now we'll head to the fragment shader. Now the first thing we note is that all of this stuff that's coming out has to come into the fragment shader. Okay, now we're going to have a sampler, and we're also, oh, what am I even doing? We'll also define the light structure. Okay, and now we can actually use that. Okay, so again, if we match this up with our queries here, the uniform is named light. Yep. And the fields are named color, position, and strength. And that's what we have here. Okay. We're also going to have fragment position. Okay. So what do we have? We're outputting a final color, yes, and I'm also going to declare a function. We're going to have a function that returns a 3D vector. Calculate point light. We'll define it down below. Okay. So the first thing I'm going to do is just get the ambient lighting working. So we'll take this, get the top 3 components. It doesn't matter, we could use XYZ here as well. They're actually 2 different aliases which do the same thing, but it makes a bit more sense here. And we'll put a multiplier of 0.2 on that, so that will darken things a little bit. So it's got like 20% light level for ambient. We'll just put that together for our final output, and we're just going to test that this works. Yep, it does work. Of course, it looks a little strange with a purple background, so we can go back, and here we're setting the clear color. Let's clear the color buffer to completely black. It's a good idea to kind of set the ambient color to something that blends in with the background color. Okay, so where was I? Now let's actually look at that function. So there are two components which we're going to add here. We're going to add the diffuse lighting and then the specular lighting. So because these variables are defined here as in attributes, and we have these uniforms as well, we kind of have global access to those, which is why we don't need to provide any arguments to the function. In fact, it's a little bit faster. We don't need to load arguments in when the function is called. It is simply just called. All right, so I'll start with just the diffuse lighting. And for that, we will need the direction vector from the fragment to the light. So again, a direction vector is our end position minus our start position. We're also going to use that to find the distance so that we can attenuate things based on distance. Okay, so we'll have vec3 called result, which will be returned in the end. And what will we do? Well, we'll take the light color times the base texture, so that will blend in that wood texture with the red light. And we want to take the dot product, and it's the dot product between the light, not the light normal, no, sorry, the fragment normal. Multiply by the strength of the light and divide by the square of the distance. In physical terms, light has quadratic distance fall off. But there's an issue here, and the issue is that dot product can be negative. So if we think about some cases, if the surface is facing directly at us, then, or directly at the light, then the direction to the light will be completely parallel to the direction of the normal, and this dot product will be 1, will be maximized. If the surface is 90 degrees to the light which is shining on it, then the dot product between the surface normal, fragment normal, and the light will be 0. If, however, the light is directly behind the surface, this will be -1. So to deal with this edge case, we'll take the maximum of this and 0. So if it's less than 0, it will be capped at 0. Okay, let's give this a shot. That's okay. Looks like we have some errors. Well, fragment position is defined, but maybe we need that. Also, of course, there we go. Okay. Yeah, so the light is somewhere here and it's shining on the surface, and the intensity varies according to how parallel it is with the light's direction. If I pretend I'm the light looking here now. That's cool. Okay, let's add the specular component. Okay, so with diffuse lighting, that shines onto the surface and it's simulating rough surfaces. So with rough surfaces, it pretty much blends in with the texture. However, with a really shiny reflective surface, it pretty much just shines off at the light's color. But to make this more obvious, I'm going to replace this with a white light. So we're not going to have the base texture. And we'll still have the dot product. That looks good, but we're going to need a little bit more. Okay, so like I said, for a specular reflection, that also depends on where the camera is, where the player is, looking at the fragment. So we'll get that direction vector there. And then if we add these two together and normalize it, this produces a vector which is halfway between those two directions. And what we need to do is, if we're in a fully reflective situation, that half vector will be fully parallel with the surface normal. So we'll run with that. Okay, let's give this a shot. Yeah, I mean, it kind of works. But we can make it more shiny, basically. So this is producing some number between 0 and 1. If we raise that to a power, that will tighten it to a point. So for instance, if we raise it to a power of 32 and run that, then it starts to tighten in a little bit. And then we'll just experiment with this. So if we raise it to a higher power, then it should tighten up even more. And we can do this to simulate how shiny the surface is. Let's wait for it to come around again. Yeah, so it starts to look more like a point. Let's make it really shiny. It doesn't have to be powers of 2, I just like powers of 2 for some reason. Yeah, there we go. So this is a really glossy surface here. See, okay, cool. So that's all well and good. But then the next question is, how do we add multiple lights? Well, we kind of have set it up already with a vector of light objects. We'll go back to the scene and add a whole bunch more. Copy paste that there. So essentially we have a red light, a green light, and then a kind of teal light at various positions. And then I'm going to go back to the engine. And I want to set this up so that I have... So I'm going to set this up so I can handle at most 8 lights. So I'm going to have the positions of 8 color locations, colors, positions, and strengths. I just need to go to config and include the vector library, array library, I mean. And then that's good. Okay. And now I just need to set these Okay, just double checking. Yep, that looks good. So essentially we are querying these. We're going to have an array of 8 light objects. So we're going to have like lights number 4 color, lights number 5 color, and so on. And that's what we're building here with this string stream. So now we're going to put this into, oops, not position 1, position I of each of these. And the thing we're going to put in is call string, and then turn that into a C style string, so a character array. And yep, there we have it. Okay, so more or less the way we're going to use these locations, if we go down below, so we're just going to select location I for each of these, and then this will just send it in. Of course, we only have 3 lights, so this will only fill 3 of the structures in the uniform. 5 of the structures will be unallocated, but that's okay because default values for unallocated things are simply 0. So a light with 0 light, 0 color, 0 strength, it's fine. It's fine. It's more efficient to keep the shader simply outputting 0 than to loop through things. It doesn't speed things up. So then we'll go back to the shaders, and now we'll have oh yeah, good point. Just double check that. Yeah, that's lights I'm using there. Yep, good. Okay, yep. So now this is called lights. It's an array of 8 of them. And what we're going to need is we're going to need for our input an integer, which is the light index that we're drawing. So we'll go put that in. Okay, great. Now, again, it's more efficient to pass in just a single little data bit because this uniform is already populated with all of this stuff. So it already exists. We're simply accessing it. We get the position. Color, strength. You can see what we're doing here. Okay, I'm going to try that out. Oh, I can see the error already. Yeah, it's complaining because we need to specify that. There we go. Okay, so yeah, we have a bunch of lights. And each of them have highlights, and sometimes those highlights are easy to see, sometimes not so much. There we go. Yeah, it's cool. That's cool. Okay, so that's how we can do lighting. We start with 1 light, then we build up an array of many lights. Some devices, I think, have a limit of 8. And 8's pretty good anyway, because this can be reset on a per object level, per object basis. So if we have a bunch of objects, we can keep track of which lights we want to affect that object, load that data in, render it, and then load in data for the next object. Okay, anyway, that'll be it for now. Hope you enjoyed, and I'll see you again soon. Bye.